Looking at the worksheet problems for chapter 4, we have 2 of them, and let's get going. Problem number 1, a rugby player is being pushed backward by an opposing player, exerting a force of 800 newtons on him. The mass of the losing player, the one that's getting pushed backward, plus equipment is 90 kilograms, and he is accelerating at 1.2 meters per second squared backward. And we have 3 questions. Number 1, what is the force of friction between the losing player's feet in the grass? 2, what force does the winning player exert on the ground to move forward if his mass plus equipment is 110 kilograms? And 3, assuming that the force between the 2 players is horizontal, find the coefficient of friction between each player and the ground. First question, as always, what's the concept? So in this case, we have forces, we have acceleration, so Newton's second law is our concept, and we're going to have to also apply friction as one of our forces. So draw a sketch of the problem. There's my sketch. Draw a Freebody diagram showing all of the forces acting on the losing rugby player. So I'm only showing the forces acting on player 1. So player 1 is this guy. Player 2 is that guy. So I'm going to show all of the forces acting on player 1. So first, force gravity 1 equals m1g. Force normal 1 equals, well, we'll find it out. Because he's trying to push forward, we're going to have force friction 1 going forward. And then finally, we have player 2 pushing on player 1. So we have force of player 2 on 1. So there's our Freebody diagram for player 1, only showing the forces acting on player 1. Any astute student knows that there is an equal and opposite force of player 1 pushing on player 2. But that's not acting on player 1. That's acting on player 2, so it's not included here. Likewise, the force of gravity, the force normal, the force of friction on player 2, those are not here because they're on the wrong object. So now if we were to do the technical Freebody diagram, we have a dot for player 1, and then we show those forces. Force gravity 1 equals m1g. Force normal 1, don't have a value for that. Force friction 1, and force of 2 on 1. So there's my Freebody diagram. I've got all the forces, so let's list those forces. Force gravity 1, force normal 1, force friction 1, and force of 2 on 1. So I'm going to break them into components, so I'll have force gravity 1 in the x direction equals force normal 1 in the x direction equals force friction, that's not an F, force friction 1 in the x direction equals, and force 2 of 1 in the x direction equals. So if I look at my picture, everything is already broken into components. This is going to be easy. Now I drew this here just so it's on the same picture so I don't have to go back and forth. So I have, and I want to make sure I put them in the same order, gravity normal. Force gravity 1 equals, in the x direction, 0. In the y direction, now I said 0. Before I can do this, I have to define directions. If there's an acceleration, you choose one direction to be parallel to the acceleration. This has acceleration. The feller is accelerating backward, and so there's my x and y directions, just the standard, and we know the acceleration is in the negative x direction. So now that I've done that, I can continue on. The force of gravity in the y direction is minus m1g, and the force normal 1 is all in the y direction, so 0 in the x direction and normal 1 in the y direction, that's pointing up. Force, did I do friction? Yeah, I did friction first. Force of friction 1 is equal to, that's positive, mu, and I didn't specify, obviously he's sliding so it's kinetic, but let's just put mu times normal 1 in the x direction, 0 in the y direction. And force of 2 on 1 is equal to, it's in the negative, minus, and I'm just going to call this, I'm just going to call it A, and 0 in that direction. Why do we make our forces in such a table? so I can apply Newton's second law in each direction. Why did I choose the coordinate directions I did? So the acceleration in the y direction is 0. So this becomes a fairly simple minus m1g plus n1 equals 0. So n1 is equal to m1g. Now I come over to the x direction. Sum of the forces in the x direction is equal to m1 ax. I should have put subscript 1. Why do I put m1 ax? Because my object was object 1, which has mass 1. I always have to have the mass of the object I'm looking at there in my Newton's second law. So now I'm going to add up the things in this column. So I have mu n1 minus a equals mass 1 ax. Now what am I looking for? I better come back and redefine things, and let me fill in this table for completeness. So just filling in what we've already written down. 0 minus m1g, 0 n1, mu n1, and that was minus a, 0. Okay, apply Newton's second law in the y direction to find the normal force acting on player 1. So we've already done that. We know the normal force is m1g, and m1 was 90 newtons, so that's going to be 90, or not 90 newtons, 90 kilograms. Ooh. Times 9.80 meters per second squared. That's just using the equation that we've just determined right here. So 90 times 9.8 turns out to be 882 newtons. Now apply Newton's second law in the x direction, and we have this equation. If I solve this for a, I have a is equal to mu n1 plus m1 ax equal to mu, well, yeah, I could put in the number, but I'm actually going to put m1g plus m1ax just to make it very clear how this comes out. Factor out the m1, and that's my equation for the force between the two. M1 is 90 kilograms. And force of friction acting on it. Oh, I should have paid attention. That's not what I'm supposed to be solving for. I'm supposed to be solving for the somehow I believed I had solved this before, and I am now at a loss. Apply Newton's second law in the x direction to find the force of friction acting on player 1. So, oh, I have A is 800 newtons. I gave that number. So that's how we do it. This mu n1, that's the force of friction, is equal to m1 ax plus 800 newtons equals 90.0 kilograms times the acceleration. Now, what was the acceleration? The acceleration was 1.20 meters per second squared backward, so it's a negative. And then plus 800 newtons. So if I multiply that through, 90 times 1.2, 9 times 12 is 108, right? So that's minus 108 newtons plus 800 newtons is equal to 692 newtons. Now we're going on to looking at a Freebody diagram for player 2. So for player 2, we're going to draw a Freebody diagram on them and do the same work. So now for player 2, I will have, and I'm not going to draw player 1 in this diagram, I'm just going to draw player 2. And the forces acting on player 2 are going to be force of 1 on 2, force gravity 2 equals m2g, force normal 2, and force friction 2. And if I want to put those as a technical free body diagram, and like I said, don't need to do this, what I have written is already sufficient. I'll do this and make it so it comes to it. And so now we're going to break that into components just like we did this one. So using the same definitions for x and y direction as before, and those, because the two are together, they're going to have the same acceleration. So I now know from my previous work, acceleration in the x direction, well, actually from what's given is minus 1.20 meters per second squared. That's not special. That's already given to us. So let's just do the work. Force gravity 2 in the x direction is equal to 0, because gravity's in the y direction, minus m2g in the y direction. Force normal 2 in the x direction is 0. And in the y direction, it's normal 2, whatever that turns out to be. And then force apply, well, force of 1 on 2 is equal to plus a this time, because the force applied is going to the right. Remember, it's equal and opposite. So that's going to be 800 newtons positive, 0 in the y direction. And force friction 2 is equal to, now the friction is in the negative x direction, so minus mu2, I should have used mu1 here because they don't have to have the same coefficients of friction, times normal 2 and 0. As always, we did this so we can apply Newton's second law. Some of the forces in the y direction is equal to m-a-y. We chose our direction, so the magnitude of the acceleration in the y direction is 0. And so applying that, I have minus m2g plus m2 equals 0. Thus, m2 is equal to m2g. Coming over to the x direction, and notice again I had to use m2 because now I'm looking at the forces on object 2. And so when I add up the things above, I'm going to have 800 newtons minus mu2 normal 2 equals m2ax. So solving for this, I have mu2 normal 2 equals 800 newtons minus m2ax. Now ax is minus, so it's going to turn out to be a bigger number. 800 newtons minus m2, which was 110 kilograms, if I remember correctly, times my minus 1.20 meters per second squared. 11 times 12 is 121, right? So this is going to be equal to 800 newtons minus times minus is plus 121 newtons. is equal to 921 newtons. So that should be my force of friction 2. And it's actually in the negative direction. So I throw my sign there just for the direction of the friction. So let's go fill in the blanks. So the forces we had were force gravity 2, force normal 2, force friction 2, and force of player 1 on 2. So force gravity 2 in the x direction was equal to 0. Force normal 2 in the x direction, 0. And force friction 2 is equal to minus u2 normal 2. And finally, force of 1 on 2 in the x direction is equal to plus 800. Looking in the y directions, force gravity 2 in the y direction is equal to minus m2g. Force normal 2 in the y direction is equal to normal 2. Force friction 2 in the y direction is 0. And force 1, 2 in the y direction is equal to 0. So applying Newton's second law to find, in the y direction, to find the normal force, we found it to be force normal 2 was equal to m2g equals 110 kilograms times 9.80 meters per second squared, which turns out to be 1,078 newtons. And applying Newton's second law in the x direction to find the force of friction acting on player, well, we already calculated it out, and we got, where did we get it? We got 921, whereas my work before was different. Oh, I'm looking at the wrong thing. I had 908. Did I do my math wrong? Is correct and one is wrong. Okay, 11 times 12. 11 times 12. I am suddenly really doubting myself, which of course is a bad thing. But 10 times 12 would be 120, so it can't be 121. What am I thinking? I have 110 times 1.2. It's 132. Wow. I don't know what I did before, but that's not what I got before. And if I calculated the that should be right. Well, who knows what I did before, but I believe that's got to be right. 800 newtons plus m2 kx. Well, plus minus 50%. So 932 newtons. Now use the normal force and the force of friction to calculate the coefficient of friction for each player. So remember, my coefficient of friction is equal to the force of friction divided by the normal force. So mu1 is equal to force of friction 1 divided by n1, which is just from the numbers that we've already done. Force of friction 1 was 692 newtons. And the force normal 1 was 882 newtons. So if you divide those two, you get 0.7846. .75 to 3 sig figs. And now for case number 2, where clearly D4, 10 times 9.8 is 1078. Yeah. Change color here just so it's clear that we're doing something different. So the force of friction 2 was, I'm checking all of my numbers from previous calculation. That minus, aha, B4, not B3. Yeah, that comes out right. So 932 newtons, force of friction, divided by 1,078 newtons, force normal, and we get 0.865. So there we have the coefficient of friction for each one, and we've made some calculations about forces of friction and whatnot. So that's problem 1. Moving right on to problem 2. 2 teams of 9 players each engage in a tug of war. So we have 2 teams facing each other. Each of the first team's members has an average mass of 68 kilograms and exerts an average force of 1350 newtons horizontally on the ground. Each of the second team's members has an average mass of 73 kilograms and exerts an average force of 1165 newtons horizontally on the ground. What's the magnitude of the acceleration of the 2 teams? What is the tension in the section of rope between them? So the concept is, forces, does it give me, I'm going to find acceleration from forces. That's Newton's second law. So draw a sketch of the problem. So for my sketch, I'm going to combine all the players into one. So here's team 1. Has 9 players, so the mass is equal to 9 times the average mass of a player on team 1, which was 68 kilograms. And of course, that's mass 1 for team 1. And then we have the force of friction. The average force of friction for every member on team 1 is 1350 newtons. So team 1 is pulling back. So I'm going to have force friction 1 is equal to 9 times that number, 1350 newtons. And of course, I'll have force normal 1, force gravity 1 equals m1g. And they're being pulled by force tension 1. Now, if I look at team 2, here's team 2. That's a there, it's hard to tell. Mass 2 is equal to 9 times the average mass of a player on team 2, which was 73 kilograms. And the force of friction, these guys are pulling backward. So the force of friction on these fellers is going this way. Fellers, could be ladies too. Equals 9 times their average force of 1365. Force of gravity 2 is equal to m2g. Force normal 2. And force tension 2. Now remember, force tension 1, the magnitude thereof, is equal to tension is equal to the magnitude of force tension 2. Because when you have a rope, it distributes the force on anything it touches in the direction the rope leaves with the magnitude equal to the tension. So I have the relationship between those two forces already set for me. So here I have the diagrams for each team. But let's look at the instructions, because I think I'm supposed to start by considering both teams. Yes. So it says to draw for both teams. So here's both teams. They have the internal force of tension that's adding up to 0 because it's now internal. Based on what we wrote above, you can see that if force tension 1 and force tension 2 are both included, they add up to 0. And what I have is force gravity equals m1 plus m2 g, that's the downward force. And my, well, I still have force normals. I'm going to draw them as separate here just to make them clear. And then I have these two forces at the ends. Force friction 2 is equal to 9 times 1365 newtons. Force friction 1 is equal to 9 times 1350 newtons. Decide on my directions. Well, once again, it's accelerating in the horizontal direction, so it makes sense to make X and Y like that and that. So here's my free body diagram. If I want to be technical, I will have force normal 1, force normal 2. I put them separate. So there's all of the forces that are acting on the teams combined. So draw a free body diagram showing all the forces acting on both teams. List the forces below. The forces acting on the teams are, and so I have force gravity 1, force gravity 2, force normal 1, force normal 2, force friction 1, force friction 2, force tension 1, force tension 2, but these are internal, so they're not listed there. Now, if you look at this, that's 6 forces. How am I going to put this on here? Well, I'm going to put this on here by combining the forces as I can. So I would have force gravity combined, in the x direction is 0, in the y direction it's m1 plus m2 g. And the force normal combined in the x direction is 0. The force normal combined in the y direction is equal to m1 plus m2. And then the force friction in 1 in the x direction is minus 9 times 1350 newtons. And the force friction 1 in the y direction is 0. Notice I did not split these out. Force friction 2 in the x direction is plus 9 times 1365 newtons. And force friction 2 in the y direction is 0. And then I don't put the tensions because those were crossed out. So, apply Newton's second law in the x direction. Well, in the x direction here, just taking this column, sum of forces in the x direction is equal to mass 1 plus mass 2, because it's the combined teams, AX. If I add up those columns, I have 9 times 1365 newtons minus 9 times 1350 newtons equals, and then my M1 is 9 times 68 kilograms. My M2 is 9 times 73 kilograms times AX. So now I can just solve for AX by dividing. So let's combine numbers. What do I get when I put these all together? I'm going to get I have to do this. I did not do them previously like I should have. So if I add them together, the combined mass is 612 for the team 1 and 657 for team 2. So combined, that's 1269 kilograms. And the combined forces are going to be 12,150 for team 1. That's the second one, the negative. And 12,285 for team 2. And so when you combine those, remember it's subtracted. So the team 2 minus team 1 gives me 135 newtons. So AX is equal to 135 newtons over 1269 kilograms. And that should be 0.1064 meters per second squared. Now, how many sig figs do I have here? I have, it looks like 2. So with 2 sig figs, that's going to be just 0.11 meters per second squared. Now choose one of the 2 teams and draw a Freebody diagram showing all the forces acting on the team. So I did both teams up here, team 1 and team 2. So I will arbitrarily just choose team 1. So I've got my forces all shown. The Freebody diagram for team 1 is going to be, there's team 1. I have force gravity 1 equals 9 times m1, well, equals m1g, where m1 is equal to 9 times 68 kilograms. Force normal 1, the force friction 1, and force of team 2 on 1. So now I'm going to put those forces in here. So I'm going to have my gravity, Fg1, my normal, Fm1, my force of friction 1, and the force of team 2 on 1. Breaking those into components, force of gravity 1 in the x direction is 0. Force of gravity 1 in the y direction is minus m1g. Force normal 1 in the x direction is 0. Force normal 1 in the y direction is normal 1, whatever that turns out to be. Force friction 1, the x direction, is equal to, and if you look at the picture, force of friction was in the negative direction, so minus mu1, normal 1, in the y direction, force friction y, friction 1y, is equal to 0. And finally, force 2 and 1 in the x direction is equal to, and we found that to, no, we didn't find that, is equal to unknown, so call it A. And force 2 and 1 in the y direction is equal to 0. So with all this, we now apply Newton's second law in the x direction to find the force of tension between the teams. So I'm just going to take the x direction according to this. Sum of the forces in the x direction is equal to, oh, I should have put T here, not A. I'd actually defined that up above. Yeah, sum of the forces in the x direction is equal to Now, if we look at this, mu1, n1. Well, how big is n1? I really need to do the y direction. I didn't give the instructions here, so this is one where you have to step outside the box. Some of the forces in the y direction is equal to ma in the y is 0. So I'm going to have minus m1g plus n1 equals 0. So n1 equals m1g. Oh, wait, I forgot. I do know what the force of friction is. I didn't need to do that because I already know what the force of friction is. 9 times 1350 newtons. I'm doing that. So if I multiply that, well, so I'm looking for t, so that means t is equal to m1ax plus 9 times 1350 newtons equals mass 1, 9 times 68 kilograms times the acceleration in the x direction, which we just found above to be 0.106 meters per second squared plus 9 times 1350, which we actually calculated previously to be 12,150. So if we multiply those through, the 9 times 68, of course, we've already calculated that's 1269 times 0.10638 is, I didn't calculate that. I should have known, though, that was 135. No, that can't be it. Yeah, I multiplied the wrong number. It's not the 1269 that was combined. It needs to be the 612, which is 65.106 plus. So if you add those together, 12215 newtons. Of course, we don't have anywhere close to that in these sig figs. It's just the 12 that we have. But I'm keeping the additional digits just to differentiate between that force there, the force that they're applying with their feet, and the additional amount that's coming from the tension. So there we have finding the tension between the two teams. If you come back and look at this, the tension is 12,215. Team 1 is applying a backward force of 12,150 newtons. So that means their backward force is less than the forward force being provided by tension. They're being pulled forward because the net forward force. Team 2 is putting a force of 12,285 newtons, getting that from the ground, and the tension is pulling them 12,215, so they're going in the direction that they're pulling because the direction they're pulling, there's more force than the direction of tension pulling them. So you can see how it plays out. The biggest key to winning the tug of war is this right here, how much force you're getting from the ground. As a general rule, when you have the college kids in the gym, the team that has more mass has a higher total friction they can get, and each person's basically pulling until they slide, right? So the team that's heavier should have the advantage and is most likely to win. All right, those are problems for chapter 4.